Thank you for joining us back. I hope you enjoyed our keynote conversation, and I would like to welcome Christian Eltzschig from ekxide, who is going to talk to us about iceoryx, which I now know how to pronounce. So iceoryx2, which is a Rust-based application, but you've added some C++ and some Python to it.
Exactly.
So we're going to talk about Rust. We're going to talk about Rust's interoperability and how it's building iceoryx2 with Christian from ekxide. So thank you very much.
Thank you. So, hello and welcome to my talk, Breaking Language Barriers with iceoryx2. And I read an article some months ago, and it was stating Rust or C++, and it stated, no, it's Rust and C++. And I think this is a very nice sentiment, and I want to also, let's say, build up on this sentiment and say, okay, we can use Rust in our library, for instance, to connect Python, C++, C, and maybe in the future also other languages. And I want to talk how to realize this and building bridges with Rust. So first about me, I'm Christian Eltzschig, also as Elfenpiff known on GitHub, also on Reddit. I'm a core iceoryx maintainer since over 8 years, and one of the founders of ekxide. We founded ekxide because we wanted to really go through with our vision with an open source, safety critical library, and with our former employers, it was not possible, so therefore we created our own company. We classically bootstrapped it also and tried to get rid of any kind of venture capital so that we can really pursue our dream of creating a sustainable business with or based on iceoryx. And the company provides commercial support and feature development and so on. So therefore, if you have interest in iceoryx or iceoryx2 and you are thinking about support for it, just talk to us. This is how we finance our open source work. And now to iceoryx. iceoryx is in the end a zero-copy communication middleware. It's completely written in Rust, but it originated actually in Bosch in 2019. It was written there in C++. And at some point in time, we realized that we hit some walls when we want to really certify it easily. And therefore, it was mandatory to refactor the whole code base. And when you have to refactor the whole code base, you can also try out a new language. And this is how we came up with Rust. And since then, we also made some quite interesting experiences because we endured ESLD certification with C++, and now we are facing the same challenge also with Rust. Now you see the little differences and how easy it becomes when the Rust compiler takes away some of the problems. And again, it's very fast, and here you can connect, let's say, different processes with each other. And when you should use it in the end, if you are a high-frequency trader, if you are creating a robot which drives around and maybe can hit a human being, so therefore need a safety certification, or have real-time requirements, iceoryx2 is the library for you. So, but I do not want to talk about, let's say, safety certification today, but I want to talk about a different topic, because the nice thing about open source is if everyone uses you in use cases you never thought of. For instance, we have a game engine which is using us. We have some ships which are building iceoryx2 in there. We have high-frequency trader, which we never thought of. Why should they use a library built for autonomous vehicles? But they use it. And one thing which came more clear is that the people are also using us to avoid writing language bindings. Therefore, assume you have a library, or let's say a big system, which is written with multiple libraries, with multiple, let's say, developers that are experts maybe in Python, one in Go, and so on. And they all have their particular reason to go and write in this language. And now we have to create a big project out of it. And of course, you can start with language bindings and then start writing, let's say, bindings for C and C++ so that you can call this in, from Rust. But another approach is you can use inter-process communication and talk to them directly, and also gain some benefits you have when you have at your end a library which is intended for mission-critical systems. And now, even if you write a desktop application, you get some of these stabilities and benefits from it at your system. And I thought we'd do this together in a real-life example and do some brain surgery. So therefore, we take a look at a robot's brain and just wiring it together. First of all, let's meet Larry. This is Larry, is our demonstrator. And on top, it has a little webcam. Then it has a stereo camera, a tracking camera, and an ultrasonic sensor. on front, and then also an emergency brake system. So therefore, and it goes too close to a wall, it just brakes so that you do not hit the wall. And now, let's assume we have a customer, and they say, yeah, I want to have the next generation of Larrys. I want to have a swarm of Larrys that explore the world, but I have some constraints. You convinced me, Rust is awesome, so let's write every new code in Rust. But we have a C++ object detection library, which is ASIL-D certified. It was extremely expensive. We do not rewrite this. And this is, let's say, the reward which we always encounter, that you have to work with existing libraries. Then you maybe have also a C library, and for whatever reason, you have some users which wrote together some UI in Python, and you also want to reuse it because it's already written, everyone likes it, why should we rewrite it? We do not have any kind of safety requirements here. So how do we require, or let's say, wire everything together? We could do this, let's say, by writing language bindings, so therefore we can decide, should now the C++ code call the Rust code, or should the Rust code called C++ code. But here the thing is, as soon as you go over these language barriers, you also inherit some of the weaknesses of the languages. And maybe you do not want this with Rust and want to avoid this and want to also have maybe a different approach where you can maintain the full feature set of Rust and also use, let's say, a library which is mission critical, so to build a more robust system out of it. And also, when you now think you have multiple languages out of it, in such a system, maybe you add even Go to it or C# and so on, you have a combinatorial explosion if everyone should be somehow interoperable with everyone. So therefore, you need a different approach here. And one approach is you have some kind of inter-process interface which you can communicate with the individual processes and then, connect them. And this is what we are doing here. First of all, I want to define what a service is, which is, let's say, the most fundamental building block in iceoryx2. It's a thing which has a unique name, for instance. It can be called camera or radar or whatever you want to call it. It has a specific messaging pattern, publish, subscribe, for instance. If you have a sensor which just sends out a stream of sensor data, you have request response. When you, for instance, say, hey, robot, drive from A to B, then you have a request, and then the robot maybe gets a response or sends you a response where it says, yeah, I'm going now to B, and now I have arrived at B, for instance. And Blackboard is a more advanced messaging pattern, which is like a key value store, and then we have also the events in there. Something which we are able to do, because we are working only on one system, is to really separate data flow from control flow. This is something which is you are most of the time not aware of when you use network protocols, because it's always merged together. You send a network package, and then you have maybe a low-level syscall like select, epoll, IO notify, and so on, which wakes you up and says, here's data. But in the end, these are two distinct things. Sometimes you have maybe a platform where you just want to send data, but on the other side, you have a 3D engine which just pulls over in an infinite loop and doesn't care for event notification, just takes what's there in the queue and then just renders it, for instance. And this allows us to have a much lower latency and can avoid, let's say, for instance, syscalls on a hot path. And the event, for instance, is something which is a control flow pattern, meaning you can orchestrate different processes with it. You can say, for instance, okay, this process has now something discovered interesting, like the ultrasonic sensor detected, oh, the wall is closed. I just wake up the emergency brake and say, hey, by the way, check here the data which I've sent you. You should maybe brake. And then it wakes explicitly up, and then it can consume the data you have sent there and then do what emergency brake does. And also, all the services are strongly typed. And here I wanted to show how to use really actual structs in Rust and C++ and how to make them work together. But also, sometimes you have to use serialization. So therefore, if you want to use serialization, a byte array, which is just like a slice of U8s, is also a strong type. And then you can just do your serialization in there. This is also possible. So we start with our new code, which is written in Rust, and say, okay, we have here a camera service, and this camera has struct for full HD camera with 3 values for the colors, and we want to send it from our publisher, which is our camera driver, to subscriber. How we do this in Rust and with iceoryx is with this little piece of code. In the end, the first line just states, okay, we use iceoryx2. Then the next thing is we create a node. The node is in the end one of the communication endpoints in iceoryx2. It's then a factory for our services, and therefore we start with creating it. And then when we have created our node, we can create a service we call camera because we're publishing camera data. We make it strongly typed by saying, okay, it's a publish subscribe messaging pattern, and we want to publish camera data here. And then we just open or create it. If it's already existing, we just open it, and if it's not existing, we create it. And then we want to have some construct to send the data, and this is our publisher, which we create in the next line. And now we have set up the whole communication process. And now we want to send data, so therefore what we do is we go to the publisher and call loan uninit. What's happening behind the scenes, I will explain later, but in the end we go to a shared memory allocator and say, give me memory, which is uninitialized, so that I can initialize or write my camera image in there and then send it out. I write my camera image in the next line, and then the sample behaves like a maybe uninit. So therefore, if I have an uninitialized value, I have to then, after the initialization, say, okay, now it's initialized, and this has to be unsafe, because you could lie, and you have to ensure that the contract is stable and that you really initialized all the data. And then, when it's initialized, we can send out the data. But now we have a problem. Our customer said that the object detector where we send the data is C++ code, so therefore we have to somehow interact with C++ now. And I'm sorry, I know it's a Rust conference, but I think also we build bridges, so therefore I show also a little bit C++ code, so that we get reminded how nice and fancy Rust looks like. But here, okay, this is now a C++ struct where we have exactly the same camera data, it's layout compatible. And now we create an iceoryx2 again, our node with C++, create our services. Here you see these little, when you write these examples and then you have a direct comparison of these languages, you see these slight, tiny benefits, like for instance that Rust has try into or has a question mark operator, which C++ does not have, and therefore you have to work with expect, for instance. And the code looks a little bit more detailed. But in the end, it's the same code like with Rust, but at the end we create a subscriber so that we can receive the data instead of sending out the data. And in the next slide, okay, now we have set up everything, so therefore now we want to use our subscriber to receive the camera data. And if there is camera data, because sometimes you as a subscriber, you can also not receive anything because there was nothing to see, for instance. So therefore we check if it has a value, and if so, we detect our objects on this image. So, but now again, we have a problem. The object, the UI, which should visualize the camera image and the objects which are detected, is written in Python. So therefore, we have to again now somehow get Python into the play here. So on a high level, we create now another service called detect objects. And it has a struct of like an object type. It's maybe a number which identifies if it's a car or a tree or a person, for instance. And then we have a box around this so that the UI can draw the triangle and say, okay, here is a tree, for instance, which I have detected. And I skip now the C++ side and go just straight to Python. And in Python, you have something called C types, and then you can also define C structs. And we do the same thing again here, so that it's again memory layout compatible, and say, okay, we have an object type, has an uint8, and we have an object box, 4-dimensional array, so that we have the boundaries of the object we have detected. And again, it looks similar to Rust and to C++. We create our node. Now with Python, we create our service. It's again strongly typed, and it's called detected objects. And then we have a subscriber where we can receive then the detected objects. And again, this code, now it's written in Python, but in the end looks similar to C++ and Rust. We try to receive something, and if we have received something, we can draw this on the UI. But what we have actually achieved here is now that we created a system based on iceoryx2, which can communicate with different processes without any kind of serialization. So therefore, we have a Rust process, the camera driver, it publishes happily to the C++ written object detector, it publishes happily then to the Python user interface. And if we go in this direction, for instance, and instead of writing a language binding, we have something now that we can say, for instance, if the camera driver or the object detector maybe crashes or can, for whatever reason, cannot publish any more images on the UI, you can just tell this to the user and say, okay, something here is broken, but you do not have a fatal crash, for instance. So therefore, you inherit some of the stability, which, for instance, is essential for safety-critical systems, where we really expand a system into multiple processes, you only get now for free. So therefore, which is quite nice. And So in the end, the summary is you have zero-copy communication between 3 languages. You do not need any kind of serialization, and this is actually extremely easy to integrate. This is something where customers come to us and use iceoryx2, and this is how also we discovered this use case, because they use it exactly like this instead of writing language bindings. So, but now the question is, how does it work underneath? I wanted to first highlight the communication part. Usually, when it comes to inter-process communication, most people assume it's some kind of network protocol, and therefore it comes with a high cost, and therefore they try to avoid this. And in a network protocol, just for fun, let's assume we have a sender and we have 3 receivers, and we have some kind of large data which we want to send to the 3 receivers. This large data could be a large camera image or whatever you want. But before you can send it, you have to serialize the data. You do not have to do always this step. Sometimes there are serialization protocols like Captain Proto out there where you can do a zero overhead serialization, but in the end you have to somehow take care of this. And then just in this example, I assumed the worst case scenario where you really have the large data, you have to serialize the data, therefore you have to invest some CPU time and some memory time to do this, and you end up, you have 100 megabyte of payload, but you're already paying 200 megabytes in your memory. And now you have to send it out to the receivers via an additional copy, and now your 100 megabyte become 500 megabytes because all of the individual processes now have to take a copy out of it, and it's even worse, it's serialized. So therefore, they have to deserialize the data in parallel, which costs you, again, a lot of CPU time, a lot of memory time, and suddenly your 100 megabyte became 800 megabyte, and it's really exploded. And then, after you have deserialized the data, you can consume it as a receiver. And this is something which you, as a normal network protocol, has to do. This is something it's not a criticism, it's just a fact. If you're communicating across boundaries of machines where you do not share any kind of memory, you have no other choice than to work like this. But if you have pure inter-process communication, or you have inter-process communication in combination with network communication, you have better alternatives, like zero copy. And the gist is that in zero copy, you have a sender, but instead of writing a copy, you have a shared memory region which is shared between all the receivers. And therefore, when the sender then produces the data, it produces the data once into shared memory, and then it just sends out a pointer to the receivers and says, hey, in this shared memory region at this position is your payload, and instead of sending 3 times 100 megabyte, you just send 8 bytes, which is, you can forget it. And even with iceoryx2, we have optimized it even further, that we do not use Unix domain circuits or message queues from it, but we just use shared memory log-free queues in there, which are in place there. And this allows us to go, have a communication without any kind of syscall, which makes us incredibly fast. So, okay, and when the receiver has received this pointer, in the end, it's a normal pointer. In the end, it's not a normal pointer, it's a relocatable pointer, but in the end, it will be translated into the process space of the receiver, and then it can consume the shared memory directly without any copy, as efficient as possible. And then you have this comparison. And how it works and why it makes sense to use inter-process communication, a library which is really specialized for it, because you do not have any kind of overhead. You can really use it as efficient as and wake up from a thread. When you have, let's say, for instance, maybe an application with multiple background threads and you use that in Signal so that the thread wakes up, it costs you around, I think, 2 to 5 microseconds, and iceoryx is even faster. Here you see a little benchmark. This is something which you observe when you compare an inter-process communication library to a network communication library. Here we just tested it with Unix domain circuits and message queues, but in the end, every network protocol is based on some kind of socket in the end, and then you have exactly this thing which you then observe. And now again, I wanted to also highlight how it works from a type perspective. How can we even make sure that they have the same memory layout? And first of all, we have to talk a little bit about processes. Processes have usually on Linux, Windows, Mac OS virtual address spaces. Therefore, a pointer which is valid in one process is not valid in another process. When you just take a look at the integer values, you have maybe process A, which has a virtual process space which starts at ABC, and then you have a pointer which points to ABD, which is fine because it points directly into the process space of the process A. But when you send it to process B, it points to nowhere because the virtual address space starts at F00, for instance, and then you have just a classical segfault. With this in mind, when when you want to send data, it must be self-contained. You are not allowed to send any kind of pointers to heap and so on, because this is not valid in another process space. And also no handles to any kind of resources, for instance, that you say, okay, I have this file descriptor here and I want to send it over to another process. We have messaging patterns for this, but you cannot use it directly, for instance, in publish subscribe. And also, with this in mind, let's assume you have a data structure like a list or a hash map or something like this. Usually they have pointers to connect all the nodes inside of the data structure, but again, these pointers become invalid if you transfer them to another process space. Well, therefore, you're not allowed to use this. But this is no problem. iceoryx will help you here with two things. First of all, in Rust, we have trades, which is a wonderful thing, and therefore we can provide a zero-copy send trade, which ensures that all the contracts are upheld and you do not violate anything. And the other thing is that we also provide more complex data types, which allows you to also to use a vector, a string, or a map, and so on, or a slot map in shared memory. So. But now the next step is we do not only want to communicate between different processes, but we also want to communicate between different processes across different languages. Like we want to send data from Python to C, to C++, to Rust, to Go, to Java, you name it. So therefore, we must ensure that the memory layout is identical. And here you have to then really be careful of the fine nuances of all these languages. You are not allowed to use, for instance, non-size types or Boolean, for instance. And in Rust, I think a Boolean has 1 byte, but in C++, it's implementation defined, as far as I know. Also, char is a size of 4 in Rust, but in C++, 1. So therefore, you have to really take care of this. But again, here's something which we are an open source project, so therefore we will also welcome contributions, but also we are working on this to make life easier so that we provide all the default constructs so that you can create these things safely. And on C++ side, for instance, they have to be standard layout and trivially copyable. But let's assume you do not trust any of this. How can you really ensure that something has the same memory layout? This is actually quite easy. This is the Rust and the C++ side. Let's assume you want to share this message struct. And on the Rust side, we can just ensure that the offset of the version thing, for instance, starts at 0, that the value starts at 8, and with this we can ensure that the offset of the individual members have the same position, and therefore we know that the layout of the memory struct is the same. And iceoryx on top of this also ensures that the alignment and the size of the data type is also the same, so therefore you do not run in any kind of undefined behavior. And here the thing is, if you use shared memory zero copy, you get also more advanced features at your fingertips, because you do not have to, let's say, handle these network problems and so on, and you can share memory between different processes. First of all, assume you have a more dynamic system, and we extend our Larry robot so that it can also detect the speed, the position, the acceleration of objects. If we want to calculate these 3 things, we need 3 camera images, not 1. So let's assume we have in our process, it starts up late, connects to the camera. Let's assume it would be a network protocol. Now we have to transfer 300 megabytes to this process. This takes a while. This is horrible for a real-time operating system. But if you only have to transfer 3 pointers, it's easy peasy. You have just a shared memory, which is shared between the sender and the receiver. The receiver connects to the sender, and then the sender just say, okay, here is the latest data. These are the 24 bytes which I owe you, via a call, which let's say via a path which does not contain any syscall, so therefore it's as efficient as possible. And with this, you can have a dynamic real-time operating system or real-time system. The other thing is, what we also use is, I said shared memory, and it did not specify what kind of memory it is. In the end, we need some kind of memory which we can share between instances, and the instance can be a process, can be also a process. Let's say we talked before in a talk, we heard the hypervisor use case, where you have a QNX host and you have a Linux guest, for instance, they are connected via a hypervisor partition. This hypervisor partition in the end is also a kind of shared memory, and the QNX process can share the memory of a Linux process, and then they have zero copy communication between them, or maybe GPUs, for instance. Okay, and this is something which we can exchange, and this makes iceoryx also, let's say, extendable and extremely modular. And we can, for instance, exchange these different memory types just by changing one line. You saw the Rust code in one of the previous slides. And when we created a node, we defined also what kind of service type we want to have, if it's an IPC service or it's a local service, or maybe here a CUDA service. And then we just use the CUDA memory allocator and the CUDA memory handles to exchange the data or hypervisor partition, whatever you can name it. And our vision in the end, what we want to achieve with iceoryx2, this is a slide I showed already in some previous presentations, and more gray boxes are now getting black. For instance, we added Python support this weekend with the latest release. And what we want to have is that you can use iceoryx without taking care of any kind of the communication overhead. So therefore, you are a developer and you want to send a camera image from A to B. You don't care how it gets there. This is the task of a system integrator or an architect and so on. You just say send with publisher, and on the other side you say receive. If you are now, let's say, on different hypervisor partitions connected via some IP, DDS, RAMQTT, or Sino, for instance, you don't care. You just want to send the data from A to B, and which is interesting for you, or let's say the process which are interested in the data should receive it. And currently also we have an RMW binding for iceoryx2, and at some point in time I hope we can achieve it that you can all use these languages, can use directly from ROS2, send some messages out there, can communicate with your AutoSAR application, with your native iceoryx2 application, and can start a gateway so that you can also communicate with your DDS application, for instance. And also that the whole thing which you see here is also certifiable. In the end, so that you can not only use it in a desktop system, but can say, start with a desktop system, write my proof of concept, but then I go over and can also deploy it safely to my mission-critical system, whatever it may be. And with this, I'm now open for questions.
Thank you, Christian. Do we have a couple of quick questions over here, Daniel, and a couple there? Okay, I see you too.
One of the things that I've encountered when doing shared memory communication in the past is the difficulty of managing the lifetime of those shared data objects.
Yeah.
What does iceoryx2 require the applications to do for that?
It's all hidden behind the API, so therefore the application has to do nothing in the end. We go even so far that we say we have a zero trust approach. Let's assume you are a rogue process and say, I don't care. I just violate everything. I try to open any kind of shared memory and write their bits in there to induce undefined behavior in another application. We avoid this with syscalls in the end with protections. For instance, in Linux, we have memory protective keys where we can ensure as long as I'm consuming the data, the other one is not allowed to write in there. The funny thing is in QNX there's not such a mechanism available. They have only mprotect, and therefore it needs to be collaborative. But let's see what the future brings.
Okay, we had two over here.
Yeah, I was also interested about security of the thingy. Well, if the memory is shared, of course, but yeah, you already answered this question apparently. But the other one is how do we manage the lifetime of the data we transfer? So for example, if the data is shared between like 3 clients, how do we know when we can release this data area?
Okay, this is something, it took us a while to figure it out correctly. We had, in the end, there are 2 generations. In classic iceoryx, we use the reference counter. If you use a reference counter and want to deploy a zero trust policy, you have to trust that one of these is evil and just writes a random number into your reference counter, and then everything is broken. So therefore, you cannot use this approach. What we now use is an approach which you maybe are familiar with I/O uring, where you have a submission queue and a completion queue in the end. What we do is we send a pointer out there to the receiver, and as soon as the receiver is finished using it sends the same pointer back to us, to the sender, which has the responsibility and the ownership of the actual data segment. And as soon as it has collected all the samples back from the subscribers or the receivers, it can then release and reuse the memory. But assume you have an evil sender and says, yeah, I don't care. I just write in there because I want to induce undefined behavior on the other side. This is where our zero trust deployment comes in, where you just say we can also guarantee that the receiver, as long as it reads the memory cannot be written to by the sender. And now we have the other use case that you have an evil receiver and does say, okay, I do not give you the memory back. But here again, in a safety critical system, you can pre-allocate memory for your worst case estimation. And with all of this together, you can say, okay, you have a system which should be safe.
But what if the receiver does not release this memory?
This is exactly, you pre-allocate. You, in a safety critical system, you assume that this receiver never release its sample. What happens is it no more gets any more messages. You say, okay, you have the maximum amount of messages which you are allowed to hold. So therefore, you get nothing more new data, no more new data. But all the other receivers are not affected by it because we pre-allocated all the memory which we require. So therefore, all the normal receivers happily receive their data, and the rogue receiver which doesn't play according to the rules, yeah, okay, it shoots himself in his own knee. So therefore, okay, he can do this.
Okay, thank you.
Thanks, it's a great library, absolutely, I love it. But one question that I had is, how do you sync the types between languages? Yes, you can check for the memory layout, but ultimately, it can very quickly turn into a union from a struct.
Yeah. Here the thing is, again, iceoryx has a version 0.7, so therefore we are not completely finished with all the features we require. But there is we are very happy that there is Zerde, and Zerde has reflect and generate. So therefore, the idea is we define the type once in Rust, and then we can use a Zerde reflect and generate to generate C++ code, Python code, C code, and so on, what all we require. And with this, we also deploy a test suite, which really verifies that all these members are at the same position. And then again, we have also an IDL directly in the service integrated, so that iceoryx2, when it connects to, let's say, things, sees, okay, they have both the same understanding of the type which they are communicating. And with this, you should be safe.
And a small question, what's the status of async support? Like?
Okay, a good question. We do not have async support, but again, this is requested by many people. So therefore, what we have at the first step is that all the constructs in iceoryx2 are now completely thread safe. You can send them between threads, and now the next step follows that we provide async API. Maybe it comes with 0.8 or 0.9, but it's on the roadmap, and we work on this.
Okay, we have a few more questions here. I'm going to take one more. I know a couple other people had their hands up, but maybe I can ask you to save it for the lunch break or socialize at Oxidizing, because we have other speakers that are coming up. So we do have a little bit of puffer to go over, but I'm going to start over here, and then we'll go into the next speaker, and maybe we have a little bit of time for questions before our lunch break. So here, quick.
So I have two questions which maybe are no longer that relevant, the second one at least. The thing is, do you support any use cases where the data needs to be copied as well? And the second question following that is kind of like, what do you do if you have components that work in a different NDNS and then you have to swap? Have you considered this in some way in design?
First of all, the interesting thing is copying data. The high-frequency traders want to do this because they have usually small data. They have just 8 or 16 or 24 bytes in the end. And then you just say, okay, this overhead of the zero copy and the point of the referencing, so therefore we want to have just like copy it over without syscalls. On the roadmap, not yet implemented. Other thing, NDNS change. We are in the process of communication, so therefore we are on one machine, so therefore the NDNS should not change. You can have via Chemo, maybe a virtualized environment where you have actually something like this, a change with a hypervisor partition, we have an emulated target with a different NDNS, but in this case, you have to do serialization.
Okay, so you're only targeting the same host, basically.
We target the same host and also the network, but here the thing is, we are not a network library, so therefore what we provide is a tunnel or a gateway which uses, for instance, Zeno, which then takes out the zero copy data from the shared memory, serializes it accordingly, sends it to another host, and then the other host just receives the data and then can continue to communicate. But here the big advantage is, we only serialize if we really have to. We just read our Zeno gateway, for instance, or tunnel, and if there's a counterpart subscribed to the same topic and says, I am interested in the camera data, then we say, okay, cool. Then we serialize the data, transfer it over the network so that you can receive it. But if there's no one on the other side, it stays local, no serialization. And then
Thank you, Christian. Yeah, as you can see, there's a lot of interest still in your topic, and I am going to have to ask everybody to save your questions for the lunch break because we do have to move on with our program now. But it does sound like maybe there's enough interest in iceoryx and what ekxide is doing that maybe you put on your own conference at some point.